Okay, let's start. So we are in the eighth week of the course. Sorry, ninth week is over, and we are in the 10th week of the course. Today we are going to discuss about week 9 and whatever the things which were discussed. So week 9 is more or like a continuation to what happened in the last week, which was bending, and it we dealt only with pure bending, such that there is no shear force in the beam, like only bending moment uh, is present. Such we developed the theory, which was initially proposed by Euler Bernoulli. So Euler-Bernoulli beam theory is basically it is applicable for pure bending cases. But in real life structures, or uh, we get shear force also in addition to the bending moment due to the live load or dead load, whatever it is. So we have to account for shear forces also. But since we are dealing in uh, linear regions, so uh, we can use the principle of superposition and take the bending stresses and shear stresses separately, and we can sum them. So that provision can be combined effects can be studied. So here in this week, we have moved on to shear, like how shear is impacting on the structure and how shear stresses are developed. So we have seen in the lecture a beam, 3-point bending problem. In that, there is a load at the midpoint of the way, and we have seen that this is what like a shear force diagram looks like. So shear force is not zero, and the bending moment is looks like this. So like a linear deviating bending moment, not like constant bending moment as we have seen in the pure bending case. So uh, we we saw how uh, we developed an expression for shear stresses along the section, along the depth of the section. Uh, we have seen that it is parabolic for a rectangular case, and it's like if there is an I section, it is like parabolic, and there is a sudden jump like this due to the reduction in depth of in the web. So distributions how we got and all, and we have also seen there is a linear variation of shear stress in the plan, and we have seen shear flow how it occurs, and we have seen in one session about composite beams, like if there are two materials, different materials joined to make a structure, how does it affect the strains and stresses? All these things we have seen. I hope you have watched the lectures.
Sir, before we starting this numericals problem, sir, I have little doubt on the theories.
Yeah, okay. Ask.
Sir, the stress professor already shown that two three joined beam combinedly when acted load is applied, then it is relative motion is happen within near the two surface.
Yeah, yeah.
So on that they show that to restrict the motion,
Hmm.
so they show that the forward stress is on the toward the direction of the flow. This is not understanding.
I didn't understand what you are saying. Forward
So
stress.
the when the relative motion is happen between the two surfaces,
Okay.
to we take a section to calculate how we for the restriction of this surface to restrict it. So professor what do the told that the force xy is acted on the same direction to stop the movement.
Okay, you are saying about this, like we have seen, we have taken a beam, and here we have cut a section,
Correct, sir.
and then we get this. If I take the top part only, and there is bending stresses
Yes,
due
sir.
to variation in bending moment. These stresses on, uh, let's say, this is distance dx.
Yes, sir.
So there is imbalance of forces. So for that, we should have some force which is acting in this direction. Uh, there should be some resistance on the bottom surface at this section, because if you integrate this, okay, and if you integrate this, you will get the net force. And taking two forces, there will be some force imbalance.
Huh, sir, that is the point. So how you take that consider this direction toward this way, the bottom
You
surface?
can, okay, okay. You can take either way, okay. It's not a problem. But here, uh, see, we have taken the axis like this, right? X and Y. So from the top, you are going in the negative direction, right? Negative direction. In negative direction, we get the negative phase. So negative phase means we will take in the negative x-axis direction.
So it is the matter of only sign convention.
Yeah, it is just sign convention. It doesn't have to be this way also. If you we just take it, after that, if we get minus, then minus of this, then the direction of the force, shear force, is in this direction. It doesn't matter. It's just a sign convention.
Yeah, understand, sir.
Yeah.
Sir, another is that sir the stress flow. So,
Shear flow.
sorry, sir,
Hmm.
shear flow, sir. The shear flow means this is only the representation point of view means how this
Yeah, it's just representation. It doesn't. It is not physically. Uh, it's not like a physically seen phenomena or something like that. They have just made uh, fluid flow is compared, like it is an analogy with the fluid flow, like how fluid is flowing. They are saying that shear is also flowing.
clear, sir. So last
Yeah.
question is that
Hmm.
so when the we don't consider the beam as a slender when we bend it, so we
Hmm.
getting a curve on the top surface. So that is the anti what is the sir?
Uh,
The curve name I said not pronounce it properly. So
okay. Curve. Okay.
so when we bend it, sir, there is a small concave curve is formed na, if it is don't consider as a slender member.
Ah, I didn't understand. Okay, okay. Ask.
Uh,
Anti-synclastic something.
yes, sir. Yes, sir.
Okay.
So so we already all we derive all the problem
Hmm.
by sectioning we take the section cross sectional of
Ah,
the beam, but
yeah.
when we consider when we take the horizontal vertical cross section,
Hmm.
so there should be a stress is generated in between na sir, it will not zero na when it will the vertical cross section.
Uh, I didn't understand. Okay, I'll draw a figure. This is a beam.
हाँ sir.
Okay. Uh, so if the beam bends like this, uh,
There
you
is
are
an
saying that,
anti-elastic curve is generated, sir.
okay, like this, something, a beam will bend something like
Yes, sir.
this.
Correct,
Uh,
sir.
uh,
So the below the sorry, below surface below portion of the beam is
Hmm.
contracted and upper portion is bulges out.
Enlarge. Yeah, yeah. Hmm.
So if we take the horizontal surface, horizontal sorry, vertical section
Vertical section means you mean
throughout
like
the
this,
no sir, no sir, throughout the axis.
like this.
No, so this is horizontal. So you rotate it 180 degree.
This is horizontal. Vertical section is this only, right? You want to cut
Sir,
this.
sir,
Okay,
you
okay,
rotate
okay.
it.
Okay,
Sir,
okay,
yes,
like
sir,
this.
yes,
Okay, okay, okay.
yes, sir.
Yeah.
So, sir, in this case,
Hmm.
the uh, in this case the shear how the shear force is zero, sir, in this case.
How the shear force is zero. So the thing is, you don't consider this curvature and all. Okay, we are not going to that. We are ignoring all these effects.
Understand, sir?
We are ignoring there is curvature and all. Okay. Uh,
Understand, sir. Sir, another
and
problem is that, sir,
yeah, and
the
how it becomes zero is, I'll tell you. Uh,
yes, sir.
because there is a beam and there is some shear force shear stress distribution. Sorry, bending stress distribution is there, right? Something.
Yes, sir.
So the thing is, whenever you take this bending stress net force, if you integrate it from my over the whole the depth, this force will be zero. Tension and compression should be zero, and this force also is zero. Okay,
Yes, sir.
did you understand?
Understand, sir. They are opposite to each other.
Yeah. See, no. See, entire this force, this is tension. Let's say this is tension and this is compression. Both should be zero. Okay, at each section. And this is tension and this compression. Both should be zero. At both these points, now we have seen that at both the sections, net forces are zero. So there is no force. So if I take a section like this, so it doesn't have to resist anything, right? So there is no shear.
Understand, sir.
Okay.
Sir, another the one doubt is that
Uh,
professor shown that the plank beam by use of the wood four wood planks.
yeah, yeah. Mm.
So, uh, so on that the second case. So where is the uh, I my question is that, sir, according to me, uh, there is two images, sir. The beam A and beam B. So beam B, if you draw, yes, sir.
Uh, like this and like this. Two
Yes,
sections.
sir. Yes.
Yeah. Mm.
So the second one
Mm.
is more no, no, the first one is more to sustaining the load as a beam, because he in the
Yeah, yeah.
second case there is the relative motion between maybe present here
No, no, no.
near this.
In first case, shear stress developed is less because you have this formula, right? Tau xy is equals to VA into y bar by IB. So this area is there, right? Here, when you bend the beam, initially only this part comes into picture, okay? And you have to see shear stress at this point because you nail them at this point only, right? At the middle of this.
Yes, sir.
Okay. So only this top area comes into picture and up to this point only. So shear stress is less here. Okay. But when you go to this, whole of this part comes into picture and nails are here.
Sir. So due to
Huh?
that, there may be the relative motion between these two surfaces.
No. Here also this nails will have shear. Okay. Nails have to resist it because uh, if these are joined like this also, beam bends, then this also there is relative motion. They
Yes,
are
sir.
nailed.
Huh.
and nails are resisting that motion. Okay.
Understand, sir.
Yeah.
Clear, sir.
But because the area is more here, so there is more shear stress. So, but it is very comparatively not a significant thing, like as it was told in the class.
Yes, sir.
Yeah.
Clear, sir.
Yeah. What else?
No, sir, that much only.
Okay. Okay. So if we have like first we have seen like if there is a homogeneous beam and there is one layered beam like two three sheets something have been put together. Both have same depths and there is the same layered beam with nails. Okay. So their layers are joined using some nails or rivets, something like that. So in this three cases, which will have the highest deflection?
Sir, the B, then C, then A.
Yeah. So you got this right? Why? How
Yes, sir.
shear is influencing the motion?
Yes, sir. Yes.
Yeah, yeah. So when layers are not joined together, they slip. There is no resistance. That's why shear is not there. That's why they tend to deflect more. So what you asked is shear flow. Shear flow is nothing but we have seen that shear flow is shear force per unit length. Shear force per unit length. Shear stress per unit length. So shear force per unit length. So analogy analogous. We are making it analogous to a fluid flow. That's it. So a beam is called slender if the length to height ratio, length to height or length to depth ratio is greater than 10, at least greater than 10. Then it is called a slender beam. And for slender beam, L by H is equals to 1 by 10. If L by H is equals to 1 by 10, the ratio of maximum bending stress to shear stress is 1 by 20. So maximum bending stress to shear stress, we have seen that this is 1 by 2 into L by H. So if I take a slender beam and put 20 here, sorry, H by L, this is so this is 1 by 20. So bending stress is 20 times more than the shear stress. That's why we always tend to neglect this shear. Okay. Shear
Understand.
shear stress we neglect in engineering analysis. Okay, I'll take a 5 minutes break, 5 to 10 minutes break. I'll come back.
Sure.
Yeah.
Okay.
Devashish, can you hear me?
Sir.
Okay, so
Yes, sir.
yeah. So the ratio of this is maximum bending stress to maximum shear stress. So maximum bending stress occurs. There is a section like this. Maximum bending stress is on the top or bottom, and maximum shear stress occurs at the neutral axis, neutral surface.
Yes, sir.
So this ratio and this ratio is 1 by 2 h by r. So for a slender beam, this ratio is 1 by 20. And next, and we have also seen photoelastic fringe patterns. Like if we have a beam like this for a 3-point bending. So in real life or in experiments, this singular point means very high stress occurs. But if we take this analysis which we have done, engineering analysis for shear stress, it shows that there is no, like, the fringes are formed like this something. But in the real life, this point is having very high stress, singularity point. And if this is only if there is no shear stress and only pure bending, we have seen that photoelastic fringe patterns are like this. So I'm just drawing it. So because the stress is linear, uh, that's why they look like this. And for axial case, there is only one color. So uh, because the stress is constant throughout the section, depth of the section. Okay. So if I have a beam with a T section, like this, and this is what the section looks like. Neutral surfaces at some depth, something. And for this is y-axis, and this is z-axis. And there is some point load acting at this point, fixed in. Let's say this point is S, and at some distance, like there is a point A, and on the neutral surface there is a point B, and at the bottom of the beam there is a point C. And on the flange, let's say there is some point D. So how does the stress tensor look like for point A?
So for point A, only the shear stress is zero, and
Hmm.
stress tensor means uh,
Hmm.
sigma. What is it? Y and Z is
Hmm.
maximum at top, that is tensile
Ah,
positive, and at C it is negative.
sigma x. This is sigma x.
Sigma x, yes sir.
Yeah. So
At
only axial force is present and every other thing is zero. Only axial stress.
yes sir.
Uh, as you said, this is compressive. Sorry, tensile
Tensile sir.
at the top level.
At the top.
And and if I take stress tensor at point B, how does it look like?
So there is a stress component, a shear stress component will come out, tau.
Shear stress component is there.
Sir, maximum there.
Ah, maximum. What about the axial stress?
Axial
Bending stress?
stress,
Axial stress or bending stress, whatever.
they both are zero, sir. Neutral
Yeah.
axis.
Yeah. So everything is zero. And this is tau xy, okay? Tau xy and tau yx. Both these are present and everything else is zero. Because this is, if you take a section that is explained and the stress is in y direction.
Sir, again, please, sir, as a the tau xy, x represent the plane direction, y
X
represent.
represent the plane direction of the stress or the
Okay,
force,
okay.
whatever. Hmm. Like so if I take a beam, this is x-axis and this is y-axis, okay, and this is z-axis, okay.
Yes, sir.
And if I cut a section, this is the section. You can see that I have cut the section on the x-axis. So the section is a plane on the x-axis, right?
Yes, sir.
Means this section has a x-axis as its normal. That's why I'm saying this is an x, okay, and having a shear stress which is in y direction. So tau xy.
Yes, sir.
For it, there will be complementary stress uh, that is tau yx. Like let's say that is in the inside. If I take a small element here, it's tau yx and there is tau xy and tau yx. Because this is in the y plane, right? Plane is in the y plane. Like you are taking it. See this plane is also y in the y direction and it is having normal as y axis. That's why this is y plane. Okay.
Yes, sir. To understand, sir, means which stress is generated tau xy, for counter stress is tau yx.
Yeah.
Sir, according to you, is there any the so this is in the 2D plane. So in the 3D in the 3D maybe a plane in the z direction also, means.
Yeah. 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 So this is a beam. Let's say whatever we have seen, you have asked that question, right? If I cut a section like this, uh, this is a z plane. This is in z, right?
Yes, sir.
So this is having perpendicular as z axis.
Correct, sir.
So I can break this beam into two parts, like this one and this one. So this is the z plane. Yeah. But we have seen that there is no shear stress there.
Yes, sir.
Got it, right?
So
Should I?
understand that. So due to that, the you don't write on the stress tensor. So all are zero. Only x and y plane you consider.
Okay. Uh, we have seen that here we have seen, right? Yeah. Is that? Yeah. Yeah. So we have seen that this at this side net force becomes zero because tension and compression should will give us zero. This force is zero and this force is zero. So if I cut a section on the z uh, direction, there will be no requirement of any resistance because the net force is already zero. So there is no shear stress developed. Okay. That's why we are taking only this also as zero, tau zx and tau xz. Okay, we'll see. And at point C, how does the stress tensor look like?
So the sigma x is so it is
Hmm.
the negative. Sorry, the negative.
Yeah, yeah. So hence we have here compressive stress. We are taking this as negative, and everything else is zero. Okay. Now look at this T section, and on the flange there is a point D. Uh, then how does the stress tensor looks like? How does it look like? Okay, on this
Sir,
point D. Have you? Can you see this point on the flange?
on the flange.
Yeah. So T section is like this. The upper part is called as flange. This upper part, and also if you have a I section, upper and bottom parts are called the flanges, and the middle part is called as web. Okay. So on the flange there is a point D. You can see this, right? D.
Yes, sir.
So
So,
at this point, how does the stress tensor look like?
so there is a shear stress is there, sir,
Yeah, shear stress is there, and also
and also the same time sigma x also is there.
yeah, tensile stress is also there. Tau xy is there.
And
Tau
that and
ix
tau,
is there. And do we have tau zx here? Tau
I,
xz? Yeah, we have, right?
yz is there, no, sir.
No, no. Yz. Yeah, yeah.
Yz
Yz.
is there.
Flange. Yeah, yz. Not yz actually.
Because sir, the stress direction toward the flange, na sir. So z and y
Ah,
direction is there, na?
okay, 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 okay.
I think so.
So yeah, yeah, I'll look. We'll draw it. So this is our flange, and let's say this our beam looks like this. Okay, looks like this, and we are cutting a section here, and on this part, this is Z plane, and this is in X direction. Okay, this is not YZ, X,
Yes, sir.
Z plane, and in X direction. Tau ZX over here. Because why does this occur? uh, for a rectangular beam, we have seen that we have uh, for web, sorry, for flange or also for flange, uh, for web section, we have seen that B and C. uh, Everything A is also okay. Tau Zx is 0. We have seen that for a rectangular wave. For I section and also for T section, what happens is that we have the stress distribution like looks like this. We have some stress distribution, let's say uh, something like this, tension and compression, and this continues like this. But on this part, uh, if I take out the flange, or if I take out the flange only, uh, you can see that, and if I cut a section, so there is stress distribution, something like this, and there is also, you can see that there is some imbalance of force. That's why there should be something which should be resisting this. That's why we have the shear force. Okay, I don't know my diagrams are making sense or not.
No, sir, it is understandable.
Yeah, yeah. Okay. For a rectangular section, what happens is that the this stresses whatever we take will give us net force 0. So there is no need of any shear stress. But here for a flange, net force is not 0. If you integrate it, there is some force, and if you integrate this, there is some force. And these forces are not equal because the bending moment is different, right? Bending moment is different at the two sections, means bending stress is also different. And if you integrate it, uh, over this section there is some force, and over this section there is some force, and in order to resist that, there should be some shear force uh, which is acting in the x direction, and it is on the z. So this is what it looks like, tau xz and tau zx. So for point D, this is the stress tensor. This is how it is populated. That is any point on the what do you say, flange, not on the top of the flange. So any point on in the middle of the flange.
Sir,
Yeah.
sir, if we consider the I section, so the both flanges are if equal, then we don't get this tau zx.
No, we'll get. Why? Why won't we get?
Because sir, they are
I'll tell you. I'll draw a diagram. Okay, this is our I beam. So if you cut a section like this, I'll get this part, flange. If you cut a section, okay. So this is this part, whatever. This part I am taking out. So shear stress distribution is there, right? And it is not giving me net force 0. So there should be something which should be resisting it, right? Some force. And also similarly, if I cut a section on the bottom flange, same thing happens. But instead of compression, there is here, instead of tension, like alternative stress, tension compression, something else will be there. Yeah.
Understand, sir. Sir, one question is there, sir.
Yeah.
Sir, we know that the I section has at the time of the loading they also avoiding the movement or the as compared to T or C section they if sir the movement is produced if it is beyond
Okay. You mean what? I mean, when you are saying about twisting moment.
sir twisting movement is produced, no? So
No, no.
you saw so you
In
see, sir.
in C section only it is produced. In that's what is in C section or all in L section. In T section it is not produced because T section is also symmetrical, right? As a vertical symmetry.
Sir, the question is that in automobile chassis, so you see, have you seen? I think so. So the below the chassis are made up of these two C sections.
Two C sections. Okay.
But sir, as compared to it should
Like
be
this,
I, na sir. Yes, sir.
like
Yes.
yeah.
No, no, sir. Only two C section. They are opposite to each other, sir.
Like this box kind of thing.
Yes, sir. Yes, sir. After some distance, another C like that. Yes, sir. They are welded with together.
Yeah. This is also like a symmetrical only. There is no twisting occurring here.
No, sir. The distance between C is more than 2 feet or more than 1 feet, sir.
Oh, more than 1 feet. Okay.
They are joined with this steel plates put together.
Okay. In between that, they are joined, right?
Yes,
Something.
sir. Yes. Yes, sir.
Yeah.
Yes.
Then it becomes a symmetrical only section. There is no twisting happening.
Okay, sir. But what is the reason behind it, sir? They don't take consider as a I only.
Uh, I didn't understand. They don't take I here. That's what you
Sir.
are
Why, sir?
asking.
Yes, sir.
I don't know, but I think they may be uh, better than I section is box section.
Okay, okay.
It
Understand,
has
sir.
more moment of inertia because the you can see that material is away from the centroid here, more away. For I section, you can see that there is still there is material near it.
Yes, sir.
Box sections are more effective, so maybe that's why. I don't know. I am not from mechanical engineering, but I am assuming that this meant where it is.
Understand, sir. So in your civil construction also, you most of time you only use this I section only, no, sir?
We civil engineering channel sections are also used. If you see, there are steel structures. In that there are mild steel beams of uh, uh, I section, L section, T sections, channel sections. Everything is used.
Understand, sir.
Yeah,
Sir, in the
but
old bridges,
uh,
in old bridges also the two plate are joined with by the rivet.
mm, mm, mm.
So the same thickness, if we go for the don't riveting, but that much amount of the same material if we take, then that is as compared to riveted, it is more stiffness, sir.
It understand. Instead of
So if we take sir two plates are 10 mm, 10
mm,
mm, we riveted it.
Okay, like you are saying this, like I have two plates and riveting it.
Sir, for your construction, I seen
Yeah,
so
yeah.
that they repeated it. So
Hmm.
instead of taking this two plate riveting, so
Hmm.
we directly take 20 and welded it is I think
Okay, you are saying that why don't you take a single plate instead of two?
yes sir because the more they all are repeated so they take
The
thick
thing
plate.
is, when industry manufactures this, because these are already manufactured things, plates and all, you cannot manufacture them in this on the site. Okay, so whenever the industry manufactures it, I think you have, I don't know if you have this design table something. But in our civil engineering also we have sections. Okay, there are some standard dimensions which industry follows. So they make these sections only uh, in these dimensions. So uh, if you want to make it customized, then whole manufacturing unit has to be like process has to be changed. So that is a difficult process. You can do it, but I think it is not feasible. So uh, that's why like sections. This whatever the manufactured things are there, they have some standard dimensions. So we cannot go beyond them. So that's why uh, I think they will use two sections and they'll revert them. But you are also saying about welding. So welding is something which is not accessible. Like you can do it on the outer part, like this. But in the middle also there has to be something which holds them together, right? So then you can also use, I think, plug welds, something kind of some sort of things you can use. But that depends on the analysis also. So yeah, but welding is more effective because welding generally gives like high resistance compared to rivets or different things. But you have to see the feasibility also. You cannot go inside the material and all. So that part is there. Standards are set. Hmm.
Understand sir so due to which we have the existing standard in our market and the production all this cost we consider and we do this go for this.
Yeah, yeah. Design decisions are taken upon that. So, and you can also see that bridges, lot of bridges, if you have seen, they have these huge I sections, like very high. It's like very deep beams. I section beams are there. I
Yes sir.
section beams will be there. If you see any bridges, railway bridges or something, you can observe this. Very depth. This depth will be very high. So these are also made fabricated, like taking different plates and different things. You cannot manufacture them in the factory and all. So you will get sections plates, and you have to again do the fabrication on the site or some other plant. You have to fabricate these girders, and then they take those girders and they put on the pillars of the structure. And on the top of that you have some concrete road, something like that. That's how bridges are also made, constructed.
Understand sir.
Yeah. These are called plate girders. I think I don't think you will hear this in mechanical engineering. They are called plate girders.
No sir it's new for me.
Yeah, yeah. And
So what is called as plate girder? So that I section or the top concrete one?
no, this I section is called as a plate girder. This one.
Oh, okay, sir.
Girder is nothing but a beam, kind of, and some other complicated things. Shear and all also you have to consider for this girder. And also you might have seen this cranes, right? In some godowns or something, there will be planes. So there will be two beams, and there is also one beam and there is some crane, okay, and this can be moved, and this also it can move from here to here.
Sir, the a gang rail crane or something they call like that.
Yeah, yeah. This also, this is also, these girders, these are also made of I sections only. These are called gantry girders. This is also, this is some, I think some more something which is more relatable to you. That's why I'm saying gantry girders. Here also I sections are used. This you can see in factory setups. That's why I'm saying. But this is also done by civil engineers only, design and all of this. We have like civil engineering has its separate course. So you might have, like, people assume, generally they assume that civil engineering was only about concrete and concrete structures and all. But steel structures also come under this, like these kind of girders and all this, and also roofs of go downs. They are also made of steel, and also I've seen airport uh, 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 aprons and different things. They all those are made of steel structures. So you cannot, like, sometimes it is not feasible to construct a concrete structure. It is very costly. So then it is preferred to use steel structures based on the cost and effectiveness.
Understand, sir.
Yeah.
Sir, in civil engineering, you use concrete, sir. So consider, sir,
Hmm.
there is a huge structure you are going to make, sir.
Hmm.
So, but in between you can't see, na, sir. The in between there is porosity is there or something there. So, but
Hmm.
how can you check all these things? Because it is so. If its porosity is there, then it is very, or air gap is something is there, then it damage the structure, sir. Sir, before
Ah.
in the dam and also, how can you means check and
Ah.
these things?
The thing is, like, whenever you pour concrete, if you have gone to a construction site, if you have seen like a slab is being laid. So whenever you pour concrete, you will see that people will be using a vibrator. So a vibrator will be there, and they will make it move on the top of the surface. You lay the concrete and you make the vibrator move on the top of it. So they will make sure that this concrete goes in all the gaps. Uh, if you compact, that process is called as compaction. Okay, to compact it properly using the standards, like there is a standard for how much time you have to compact, what kind of vibration and all you should use. All these things are there. So if you make it compact uniformly, and you follow all the standards, generally it is safe. But the another thing is that civil engineering structures also have very high factor of safety. So so if there is some uh, uh, what do you say, some construction defect is there, that also can be taken care because of this high factor of safety.
Clear, sir.
Yeah. And the thing is, whenever you do a slab or something, or if you beams or columns or something like pillars, whatever you call. So whenever the concrete batch is mixed, so they call it batches. Whenever the concrete is mixed, they take certain part of that concrete and they take it to lab and they manufacture like cubes. If you might have seen in your college, like civil engineering people will be testing those cubes and all. So they check uh, they make those tubes, and after that they check the quality of concrete. How is it resisting load, compressive strength of the concrete. So that also has to, like, some design guy has given you that this should be the strength of the concrete. So when you are manufacturing this concrete, so that also should be maintained. Like parallelly with the construction, you make these cubes and test it. So if the cubes are satisfying those strength requirements, then you can say that okay, this concrete which is used is safer for the design which was made.
Clear, sir.
So if let's say if you have a I beam like this, I beam. And this is y axis and this is z axis. A section of I beam. So how does tau xy vary along the depth of the beam? Tau xy. So for a rectangular beam, we have seen that this is what the shear stress distribution looks like. Parabolic distribution. This is for a rectangular cross section. But for a I beam, what happens? Let's say if I go from the top of the flange to the bottom of the flange, from here to here, shear stress is like this. After this, what happens? The depth is reducing. Due to that, what will happen?
Again, it will take a parabolic like.
Uh, is it continuous or is it
No, no,
having
no.
some?
Straight. Then after it will go
Yeah.
in.
The shear stress increases here at this point. Then it is parabolic because that you can see that B you have this formula, right? We have got this expression whatever. It is not working. Tau xy is equals to V A y bar. So V is the shear force and I by B. So you can see that up to the flange, this B is very high. Okay. But as you go to the web just below the flange, this B decreases. And that's why if this is decreasing, this shear force, shear stress will increase. That's why you can see the discontinuity here. And again, after that, when it goes to the bottom flange, shear stress reduces and it again goes to has a parabolic variation and it goes to zero at the end. So this is how it looks like shear stress distribution for an I-beam. What about strain? How does strain look like?
So the strain is
Hmm.
two opposite triangles.
Yeah. Will there be any jump?
Means yeah, they are. One is positive x-axis.
No, like let's say if is this linear?
Linear, sir. There is no.
Yeah, yeah. Okay, so I'm going from the top of the flange to this. Let's say I'm going from top of the flange and to the bottom of this flange. Okay, till here it is linear. Is there any jump or is there any discontinuity or is it continuous?
No, sir. The line is crossed at near the same neutral axis and extended up to.
Okay. So it looks like this. There is no discontinuity here. Strain is varying linearly and it is continuous. So
Yes, sir.
you cannot have do displacement at single point. So strain also is like that. Strain compatibility or whatever you can say. Tau Zx we have seen, right? How does tau Zx vary along the flange, length of this flange?
Tau ZX.
Uh, on this flange, how does it vary? Tau Zx.
So at the end of the flange it is 0 and at the center it is maximum, sir.
Yeah, but how is it linear or is it parabolic?
Linear, linear, sir,
Yeah,
linear.
okay. So it varies like this. Linear variation. Tau Zx.
Sir, I have question that why this tau ZX it is not look like the triangle structure, because both the sense also same, na, sir? Because the
Triangle
tau,
structure
हाँ
like
sir,
this,
so हाँ sir,
like
no,
this.
not like
Huh.
sir. So here it is maximum. Another side negative side maximum. Another is positive side maximum in the Y
Yeah,
center.
yeah. Hmm.
So, so what is the logic behind it? Why not it is go the negative maximum is not forming here?
Okay, okay. So if the like in the middle section, so if there is stress in this direction, if there is stress in this direction, okay, let's say if there is stress in this direction, something has to resist it, right?
Yes, sir.
Imagine like this. So both the stresses, that is just a convention, but you can imagine it like that. So both faces should have uh, negative direction. Then only it's like becoming zero or what, something like that. Just you can imagine like that. But I can also uh, draw you a diagram. Hmm. So if I cut a section like this here, okay, so I'll have this part and I have the other part. Okay. The other part. And this is one part of this branch. So if there is shear stress in this direction, it has to resist, right? This has to be in this direction. So you can imagine like this. But this sign convention is just for the sake of showing. You can take it otherwise, like this side as uh, positive and this side as negative, whatever.
Understand, sir.
Yeah. It's see a problem. Have a cantilever beam and having some load. at the fixed point, the free end is x. This is 1.5 meter. Of it is 1.5 meter. This is the shear force convention we follow. And this beam has a box section.
Sir, length how much? 1.5 meter.
Yeah. 1.5. This has a box section, and there is this. This thickness is 15 mm here, and this is also 15 mm. 15 mm. And this is 70 mm, and the depth, outer depth and outer width is 100 mm. Okay, and there is a point A on the top of the section, and this section is taken at the fixed end. Okay, this is point A, this is point B, and at the neutral axis there is a point C. So let's say a planar stress tensor, which is like sigma, and it is like PQ, QR, MPA. So we have to determine the value of P, Q, and R at the fixed end of the beam for the given load. So the first question is find the value of P at point A. So how do we find out? So first P is what? P is the bending stress. Bending stress is sigma x. So
Yes,
how?
sir.
So the load is applied, and due to the applied load at the fixed end, the bending moment will be 2500 into 1.5 meters. Let's say I'm taking this in mm for convenience of calculation, because I want this in stresses in Newton megapascal. So the bending moment is something 375 Newton mm. 375 into 10 to the power of 4.
Yes, sir.
This is the bending moment. Now I want the bending
Yes.
moment. Bending stress. For that, I have the flexure formula. M by I equals to F by Y. Okay. I don't know I. What is the value of I? So we will calculate I. So I is outer rectangle's inertia minus the inner rectangle's inertia, moment of inertia we do, which is 70 into 100 cube by 12 minus 40 into 70 cube by 12. So I'll get 469 into 10 to the power of 4 power 4. So I have got I have known, I know N, I know M. So M by I, and bending stress at point A, right? So Y is basically distance from the neutral axis to the point, which is 50 mm. So M is 375 into 10 to the power of 4, and This is 469 into 10 to the power of 4, and y is basically 50. So I'll get 375 by 469 into 50. So the bending stress is 39.978 NPE at point A. Okay. Now find out the value of Q at point A. So what is the value of Q? Q is tau xz or shear stress. So what is the value of Q at
Q,
point A? Point A.
that will 0, sir.
Yeah, 0. Free surface shear stress is 0. Now find out what is the value of R at point A. R. R is basically your sigma y. What
Sigma
is the
y,
value of R?
that is 0 compressive, no compressive, the tensile.
No, no, no. That is only P. R is 0. Sigma y we don't have here. Engineering analysis, we neglect whatever we take. Okay.
Okay.
Only in the axial direction we have the bending stress. In the y direction, there is no, there are no stresses. Okay. And what is the value of point? What is the value of P at point B? Which means they are asking what is the value of bending stress at point B. Bending stress at point B is just the same thing. Instead of multiplying it with 50, the distance at which the point B is from the neutral axis is uh, 50 minus 15, which is 35. So this is 27 point something, 27.9857 MPa. The bending stress at point B. What is the value of Q at point B? So what is the value of Q at point B? Which means tau xy at point B. And it can be given by the expression which we have developed, tau xy is equals to Va bar by Ip. Okay. So V we know at the fixed end shear force is 2.500 only. So there is only one load, and the area of this is we have to calculate, which is 100 into 70 minus 40 into 70. What is this? 100 into 70, yeah, 40 into 70. No, 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 sorry. So we are taking this box and we are calculating the shear stress at this point. Okay. So we have to, this area is here, this area. Okay. And that area is 15 into, what is that, 70. And y bar is nothing but the distance from the neutral axis to this point, which is again 35 divided by I. I we have calculated 6469 into 10 to the power of 4, and here the
Yes, sir. और वो मुंबई के सरकारी में पढ़ती है ना महाराष्ट्र बोर्ड मतलब स्टेट बोर्ड हाँ कॉलेज में
can you hear me?
Yes, sir.
Yes, sir.
Wait. Can you hear me? No?
Yes, sir.
Yes, sir.
1 second. I don't know why I'm not getting. Say something.
Yes, sir. Now it is audible. Hello. Hello. Am I audible, sir?
Yeah. I can hear it. Yeah. Huh. Okay. So here we are. So, see, the shear stress is at point B. The shear stress is 0.278, 0.278. But the thing is, okay, sorry, this shear stress which I have calculated is for this point and this point along these points. But here it should be 0 because this is a free surface, right? But engineering analysis says that this is the shear stress but actually because this is a shear stress at free surface should be 0. If we take this, we go through the approach which was shown in class, like using equilibrium equations, then you will exactly get that this is shear, the shear force is 0. But here, if we blindly calculate it as I have done, this will give some value, but that is not the actual shear stress at that point, because that is a free surface and shear stress is 0 here at point B. Let's say this is some, I'll say this is some point D. If this is some point D, then you can say that at this point there is some shear stress which is 0.27895 per point D. Now,
Sir,
yeah,
it should be 15 into 70 into 42.5, sir.
uh, yes, to the centroid of this, right? 30, 35 plus, in addition to that, we'll have 7.5. Since y bar is the distance from this neutral axis to the centroid of the area. So this will also vary something, I don't know what. 42.5, 0.339, 8. Okay. What is the value of r at point B? R is sigma y, and that is also 0 at point B. So this is A point, and this is B we have taken, and this is C point. So now we'll go to C point, point C. So at point C, which is on the neutral axis, what is the value of point? What is the value of P, which is the bending stress at point C?
That will direct 0, sir.
Yeah, that is 0. Sigma x at B, sigma at C is 0. And what is the value of tau xy at C? Now we have to go in the calculation again. Is V A y bar by I. So here we have to calculate the uh, y bar. Area is something like 15, 2 into 15 uh, into what is the total depth is 100, right? So let's take up to point C. This is the area which we have to calculate. This is our point C. So this is 50. This is 70. And this thickness is 15. So 2 into 15 into 50 plus. So these two rectangles I am taking first and adding 40 into 15. Yeah, 40 into 15. The y bar is, we have to calculate the centroid of this area, and that can be done. I think you have done the engineering mechanics course. Centroid, total area into let's say this is my axis to the centroid of this area is equals to, we have three parts, right? Let's say this is A1, A2, A3. So A1 Y1 plus A2 Y2. So moment of area and take it. So single moment of area. So I don't know YC, but I know for individual rectangles, I know the centroid. So let's say 2 into, I have like 15 into 50. Uh, I'll multiply this into, for both these rectangles, that is 25. Y1 is 25, let's say. And I have for this rectangle, which is 40 into 15. And this centroid is at a distance of uh, uh, 50 minus 7.5. Okay, 42.5. And done by this area again. 3 into 50 plus 40 into 50. So this YC I'll get 40 into 15 into 42.5. 50, 40 into 50. So I'll get this 30 mm. So the centroid of this area is at a distance of 30 mm from the neutral axis. This is 30 divided by I we have calculated, I guess, which is 469 into 10 to the power 4 into B. So here B, you can see this and also this, both are coming. So total B is 30. So we now go on to calculate the stress. It's 40 into 50 into 30. 30. So we'll get, so this shear force is negative actually. We forgot. You can see force is acting downwards, and the convention, according to the convention which we have seen, the shear force should be negative here. And that's why I get tau xy at C is equals to minus 1.1194 megapascal. This is the value of shear stress at points. Okay.
Sir, negative means the direction is toward.
Negative means, see, on the positive phase, my section is here, and I am going in this direction. In this direction means on the positive x-axis, whatever the force should be there, that should be in the positive direction. Then I'll get a positive shear force, because the force is acting downwards here, which is contrary to the sign convention which I have taken. That's why my shear force is negative. Okay,
Understand.
this is just a convention. You can take it as positive also, but according to the convention which was followed in the course, uh, this is the convention which we have followed. That's why I am saying that the shear stress is negative here.
Clear, sir.
Negative shear force, and that's right, negative shear stress. And what is the value of R at C? R is sigma y at, what is the value of R at C? Sigma y. What is the value of sigma y at C? This point. Can you tell?
That is neutral existence, sir.
Yeah,
0, sir.
0. Yeah. Anyway, sigma y is entirely 0. So the thing which you have asked, we have seen this wooden planks problem, right? So if it was decided to construct a wooden beam beam made of wooden planks, the beam is used as a 4-point bent beam. So with symmetrical concentrated load of 20 kilonewtons, something like this. So there is a beam which was constructed and 20 kilonewtons. And this is a wooden beam. And so the planks were like this, they were arranged like this. Here the nails are used to fix these planks. And if you see this in from other direction, you can see. So nails are there. This distance is, let's say, S. So this spacing between two nails is S. And the dimensions of the cross section are given like this. This is 300 mm and this is 200. This is 40. This is 25. Okay, so the horizontal planks are at 40, having thickness 40. The vertically arranged planks have thickness of 25 mm. So now determine the moment of inertia of the beam cross section, which resists uh, bending in power 4. So whole of the cross section will resist the bending, and we have I is equals to 200 into 300 cube by 12 minus the inner rectangle, which is 200 minus 50, which is 150 into 300 minus 80 is 220 cube by 12. So this is the moment of inertia of the whole cross section which is resisting the bending. So 316.9 into 10 to the power of 6 m1 power 4. C is the moment of inertia of the section which is resisting the bending. Now determine the magnitude of shear flow in Newton power 4 that must be carried by the screws. Okay, so shear flow is we have seen shear stress per unit length. shear force per unit length. We have shear stress as VA into Y bar by IB. Simply, if I just remove this B, that can be called as shear flow. VA Y bar by I. This is the shear flow. So, at the nails, let's say this is what it looks like. But for this arrangement, only this area comes into the shear part, and the entire remaining shear is transmitted through the nails to the other part, to the other plane. So this area is there, and the screws are present at the middle of this. So I can take only half of this area, and I have to find out the shear flow at this along this uh, along the length of the screw. So I have shear force is basically what is given 20 kilonewton. So in the middle part there is no shear force, so it only comes in this part. So that's why we will take the section is somewhere here only, not in the pure bending zone. So I have Q is equals to E is 20 kilonewton. So I will take in newtons. The area is, this is uh, we have taken 200 minus 50, 200 minus 50, 150 into, and the depth is this is 150 and this is 20. Okay, and from this the centroid of the area is at a distance of uh, 150 minus 150 minus 10. 150 minus 10 is 140 PAY bar, and I we have calculated 36.1 into 10 to the power of 6. So if we do 20 into 10 cube, 150, 20 into 140, 316.9 10 to the power of 6. So we will get shear flow as something like 26.506, something like this. Newton per mm. This is the shear flow, shear force per unit length. So units are consistent. Now he is asking what is the maximum permissible. The thing they have given is each screw has a shear capacity of 1500 newtons. Shear capacity of screw, whatever we use, shear capacity of screw is 1500 newton. So if the shear force caused due to the shear stress is more than this, then the screw will fail and the beam will fail. So we have to make sure that this doesn't go beyond this. So shear capacity is given 1500 Newton, but I have the shear flow which was caused due to the load. So let's this load, shear capacity of the bolt divided by the spacing will give me the shear flow, permissible shear flow in the screws. It should be equal to this 26.5067. So you can see that if I increase the spacing, the shear flow is decreasing. Yes, if S increases, the value of shear flow decreases. So that is not favorable. So it should be uh, above this value. This is the capacity of shear flow, and this is the shear flow due to the applied load. So this should be greater than or equal to this always. Okay, this should not go. If the spacing increases, so just because you want economy or to like waste less time, if you make the spacing more, uh, then it will not be feasible for these bolts to handle the shear flow which is occurring. So spacing can be calculated as 1500. This should be greater than or equal to. Okay, I'm just taking it as equal to 1500 by 2 over 6. Now what you will get? S is equals to 0.6, 56.589. Yeah, ma'am. So S should be less than this. S should be less than or equal to this. It cannot go beyond this. Okay.
Understand? So means the one screw fail at 1500 Newton apply of shear stress. This
Mm.
so
Yeah,
we got the 26.50 shear stress per it generated. So understand?
yeah. No. All the screws have capacity of 1500 newtons. Let's say if I have a screw, if I have a shear force of, if I apply a shear force of, let's say two plates are joined, okay? Two plates are joined, and you apply axial load on these plates of 1500 newtons, uh, then the screw will fail if you apply more than 1500 newtons. Okay.
Sure, sir.
This actually, we have only taken up to this depth, but it should be preferably taken like whole depth. Even though we take the screw at this middle part only, but this is for the whole plank. So instead of this, you can take this 1500 into 150 into total depth. So till the almost till the bottom.
Sir, we need to calculate at the point of where it is nailed, na, sir.
Ah,
So why
it is nailed. Yeah.
then why we
Ah,
take sir full length? at
Yeah, because
40?
I'll tell you. Yeah. So we generally nail at the center. Okay. But the thing is, uh, you have this section, right? For this thing, shear stress, it goes on increasing, but at the middle this is not maximum, and it becomes zero here. It is maximum at some point between the bottom part and the middle part. So it's better that we take more shear stress into calculation so that the nail can resist better.
Understand, sir. Like factor of safety, like that.
Yeah, you can say like that, because we generally know, we are assuming that it is nailed at the center, but this is also very less, so it's negligible. Like you take the whole section, it will be better. So it will give you more factor of safety. Yeah, as what you have said.
Understand, sir.
Yeah. Next, we will see. Uh, okay, we will stop the problems here. We have also seen composite beams, right? We have seen concrete. Mm. So in reinforced concrete, like in structures, civil engineering structures, you see that beams are made of concrete and also steel. That is reinforced concrete, we call it. Steel reinforced, also you can say, mild steel, because the concrete is not very strong in tension. It is very strong in compression, but in tension it is not strong. It is a brittle material, so it fails very quickly in compression. So in order to counter that, we use steel reinforcement. Wherever the tensile stress is happening, we use steel reinforcement. So this steel reinforcement, we assume that, let's say this is the neutral axis. This whole part is taking the compression, and this, we assume that the bottom part is not taking any compression at all. Sorry, not taking any tension at all, and only the steel is taking the tensile stress, entire tensile stress. So, and we have seen that this steel area we can convert into a equivalent concrete area, which is given by this area of equivalent concrete area is equals to area of ES by, sorry, C into AS. And this is called as modular ratio, something. We call it as a modular ratio. We convert this into this because we have only this, we have the flexure formula, right? M by I into F by Y. Here, if I take I as two materials, then it becomes complicated and all. So instead of steel, we are making an abstract area of the same concrete, so that the stress is also, whatever the stress we take is also linear, continuous, from top to bottom. But in reality, if I take only the steel section, this is what the stress looks like. This is also not there, but for equivalent area of concrete, the stress is less. But if I have steel, steel is taking more. Steel is uh, you are assuming that you will take more concrete area, so that this tensile stress is uh, very less compared to what it has handled. It was handled by the steel. So that's what it is, right? If I increase the area, stress will decrease. So area. So equivalent concrete section is taken like that. This is not applicable to you. I'm just saying if this thing is like wholly dealt in civil engineering, but you can also find problems like there is a aluminum beam on top, on the bottom or top of it, something like some steel thing is steel strip is added like this, and it is bonded. Then also you have to do this. You have to convert this steel area into equivalent aluminum area. Then you will get like this. So, and then after that you have to apply the flexure formula, and you get the stresses and all. You get for aluminum, let's say you get for aluminum, you get some stress here, and if you apply it with the modular ratio, you get the same stress at this point for the steel section. These kind of problems can be seen. That's what I'm saying.
Sir, here we in the
Hmm.
composite type of beam, we
Yeah,
consider the area and Young's modulus of any material is equal to area and Young's modulus of another material.
yeah. Yeah, that's what you said.
And
Hmm. Hmm.
from there we converted to at a 1 unit by considering this.
Hmm.
Okay, okay,
Equivalent area.
okay, sir. Understand, sir.
Yeah. Okay, so this is what which was discussed in the section last week. I think next week we'll go to unsymmetric bending. There is a review lecture, and what else is there? I think I don't know, next part maybe stability of structure, something like that.
Sir,
Have any doubts? Yeah.
sir, in in lecture, professor told that in I
Hmm.
don't know in Chennai or somewhere the contractor made the full bridge without using the steel rod. Then after IIT Chennai got retrofitting it. So is it so where it is, sir?
I don't know. I have also heard that in lecture only.
So means they outside put all the according to you maybe they put all outside fabricated or plated like the steel plate to
Yeah, yeah.
resist this.
Tension. Hmm.
Okay, there.
Yeah, it's not effective thing, but if you have constructed like this, you have to do make some solution, so you can do this alterations so that it resists.
Understand, sir. Clear, sir.
If you are like, especially I think Priyanka is uh, interested to go for higher studies. So our department is conducting a webinar on 28th of 28th on I think Priyanka, are you there?
Yes, sir.
Yeah. So the department of applied mechanics in IIT Madras, especially the solid mechanics division, is conducting a webinar on for PhD and MS scholars, prospective PhD and MS students on 28th of that is day after tomorrow from 5:30 to 6:30 in the evening. So In this webinar, like faculty will join, like some of the faculty from our department and solid mechanics group, and they will tell you the admission procedure, selection mechanism, and what are the research activities which are going in the department, and various career opportunities. You can also join this, and if you have any doubts, you can directly ask the faculty. So it is mm, it's a good chance. So you can utilize it. So I think if you want to join the webinar, you can see this link. You can note down this code meet .google.com. Just take this code YJY hyphen BFPJ hyphen IFR. So you can take a screenshot or also something. So you are considering this, like even if you have some of your friends who are interested in higher studies, like they have given gate and they want to go for MS, and also uh, like you also have the opportunity of direct PhD, so you don't need to do MTech and all, so you can directly join for PhD also. That is also a provision. Direct PhD is also a thing. So you are considering it, and or if your friend someone in your circle is considering it, you can tell them that this webinar is happening. If they are available, they can attend and join and interact with the faculty and get to know about the department and the research which is going on and the career opportunities, all these things. So I am just making you aware, like if you want to join, you can do it.
Sir, is it possible to copy this link and paste it in your this chat? No, it is
Chat,
an
okay.
image.
No, you just, okay. Uh, mm, don't think I can.
No, sir, it is image, sir, not Apple.
Yeah, yeah. You can just take a screenshot of it.
Yes, sir.
Can circulate it in your groups, or if you
Yes,
have
sir.
any some senior or someone. Even.
Today only I post it in my WhatsApp group.
Okay, okay. Yeah, can do it.
Yes, sir. Thank you, sir.
Yeah, yeah.
Sir, it is open to all, yes.
Yeah, open to all. Whoever is interested, they can join. It's not like.
Okay, sir.
Yeah. Even if you are not joining, if you are interested, you can join. Like, it's not that you have to join only. Yeah. It's just an information and interactive session, so that the prospective student, if someone is considering it, can get to know about the department. Outreach.
Sir, in IIT Madras, when I visit to the home page, so
Hmm.
in the mechanical, just I see the three things only. This is solid mechanics, fluid mechanics, and bioengineering. Sir, three things is there, sir? Three department is there or various is
No,
there?
no. This applied mechanics, in the applied mechanics, initially this was an only applied mechanics, and now they have changed the name to applied mechanics and biomedical. So there are three groups. Solid mechanics group is there, fluid mechanics group is there, and biomedical. This is not mechanical, okay? Mechanical department is a separate department. So mechanical department again has machine design sections, which again deals with I think solids and all. So it's like similar things, but there are two different departments.
So
But
if
this
all
is
these
more
things,
kind of our department is more kind of a interdisciplinary department. But nothing is like you can say both are same. There are different departments for different things. Focus. So there is no restriction on how which research and what research you should do. So
so directly in the home page, if I go, then I check all the departments, na, sir? So in the civil or also in the mechanical.
yeah, civil, mechanical, aerospace is there. Uh, Applied mechanics is there. all these departments are there. Applied mechanics, everything.
Okay, sir. I also saw that sir, you talk about the sustainability. They open the one branch also.